Hey folks, in this video we're going to be talking about, guess it right, vectors on vectors on vectors on vectors, y'all. So let's get started with talking about how we can draw with vectors. So as this yokel looking fool is saying, oh, a vector diagram. Yes, that's what we see here. Each one of these cars has a little vector. I suppose this car is moving this way. But each one of them has a little arrow with a V over it indicating the velocity. So this arrow points in the direction of our velocity. So remember, vectors always have a direction associated with them, and that's how we're going to show them in a diagram. So these two other yokels are pointing out, oh, hey, this car has constant velocity. It's moving the same distance each time, and the arrow on it, the velocity arrow, is consistently the same size. This other car is accelerating, so its velocity is increasing, and as it does, we're going to draw a larger arrow to represent that vector. That's pretty straightforward. Bigger quantity, well, bigger arrow, but the arrow always points in the direction of that quantity. Cool. So let's continue with the basics. Here we have a happy little sailboat. Oh, it's so cute. Well, this little sailboat is catching a breeze, and the wind is blowing at 20 miles per hour to the west. But the water that it is on, that water current, is moving 10 miles per hour to the east. So we have two arrows to represent the movement of our little boat, two vectors. Well, we can go ahead and add these vectors together by putting the little one at the tip, the tail end of the little one, at the arrow end of our long one, and we can add them together. Well, these come out, the 10 miles per hour east cancels out 10 miles per hour of that western movement. Our boat on total, its total vector movement will be 10 miles per hour west. So this is a basic way to add vectors together. These vectors are in one dimension. They're both operating on one axis. So that's pretty easy. That's pretty basic. What if things are a little bit more complicated? Let's get fancy. Now our little boat, let's say that the wind is blowing at 20 miles per hour to the west still, but the water currents change. The water current now starts flowing 7 miles per hour to the north. Well, which way is our boat going to move now? Well, what we can do is the same thing. We'll take our smaller vector and put the tail of it on the tip of our larger vector. And what we can do is draw a line that connects the two of them. And oh my gosh, we have right here, we got a right triangle. And we can do all sorts of cool stuff with right triangles. We could start by figuring out the magnitude of our measurement, and then we could also figure out the direction. Let's start with the magnitude first. So with the triangle, we can use a right triangle. We can use our friend, the Pythagorean theorem, a squared plus b squared equals c squared, and we can plug in our friends. So let's just make our big measurement a and our small measurement b, a and b, and we're looking for c, the hypotenuse. So plug those in, make some math times happen, add up those squared values, take the square root of both sides to get our magnitude. Super easy. Pythagorean theorem, ain't no thing. So we know that this long arrow is representing 21.2 miles per hour. Well, that's cool. We've got the magnitude of this vector. The other part of a vector we, of course, need is the direction. So we can figure out this angle inside there. Ba-boom! And we can use some trigonometry. So we know what from this angle, we know the opposite measurement, and we know the adjacent measurement. So we can use our friend tangent. Oh yeah, tangent. Opposite over adjacent. This is a really ugly little angle measurement thing. I apologize. That's what we're going to have throughout this video. What do you care? So we can plug in our values for tangent. So we plug in the opposite divided by the adjacent. We can do the inverse tangent function now on both sides of the equation to get just the angle. When you're doing this calculation, be sure that your calculator device is set for degrees and not radians, because otherwise you'll get an answer that is not correct. So our angle comes out to 19 degrees. Sweet. So how are we going to describe this vector? Well, it's closest to west, and the angle moves towards north. So we will say that the boat is moving at 21.2 miles per hour, 19 degrees north of west. So we are to the north of our western axis. Cool. So we got a little fancy there. Our boat was moving in two different directions. It's moving in a two-dimensional area now instead of just in one dimension, but we can handle that with some trigonometry and the Pythagorean theorem. Let's look at one more example, which is not going to use that north, south, east, west. We're just going to look with up and down. So here a helicopter flies up 20 meters and then forward 35 meters. Then it turns into a pumpkin. Then it explodes. What is the displacement of the exploding pumpkin helicopter? So in this case, I'm not going to bother having the whole four-quadrant axis, Cartesian coordinates. In this case, we're just going to use a simple XY axis and look at only one quarter of that larger chart. So we're going to do the similar thing here. We're going to put our 35 meters along the x-axis. Our larger vector is going to sit directly on an axis, and then the 20 meters vector we're going to stack on that with the tail of our 20-meter axis, 20-meter vector touching top. Cool. And then so we can make our nice line that represents the actual vector, which is the sum of these two smaller parts. Not the sum, but it's made up of these two other components. These two other vectors. I'm rambling. I apologize. Well, what are we going to do? We're going to find out the magnitude of it, and we're going to find out what the angle it is off of our horizontal axis here. So we can do our Pythagorean theorem again, plug in our friends 35 and 20, bam, bam, do some sweet maths, square root both sides, Shazam, we get that the magnitude of our total vectors be 40 meters. Great! The other thing we need to do, as aforementioned, is we're going to find the angle off of one of our axes. And we're going to go hug our x-axis because that's what we're close to in general. We're going to, if we're just talking about up and down, we're going to reference things off of the horizontal or our x-axis, and we'll see that at the end of this problem. So we'll look again at tangent because we have, we could use other functions at this point because we know the magnitude of our hypotenuse, but we'll stick with tangent and use the values that were given to us, this 20 meters and this 35 meters. So 20 meters being our opposite and 35 meters, come on, get out from under that presentation view thing. 35 meters being the measurement on the x-axis. So we can math that stuff up. We'll use our inverse tangent function on that fraction, which I just couldn't help but reduce. Made me happy inside. And bam, that spits out a rounded up 30 meters. So we have the measurement for our angle. And how are we going to describe this? Well, we want the displacement. So we'll say the displacement. And instead of using our delta x like we used before, we used that when we were working one dimension. Now we're going to use just a d, a lowercase d for displacement. So our displacement is 40 meters, 30 degrees above the horizontal. Cool. So we got fancy with some vectors. Yay! We love vectors. Here's our friend the happy sailboat. And I guess just the happy sailboat. I hope you're loving vectors, and I hope you feel pretty awesome about them now. You can check out some other videos where we'll go through some more vector problems. Ta-ta!